this lesson, I'll introduce the periodic table and the structure of the atom. We will then look at ions and isotopes once we have a grasp of nuclide notation. The periodic table contains all known elements, and these elements are arranged in order of increasing atomic number and are grouped by their chemical properties. A row is called a period, and a column is called a group. All elements in the same group have the same number of outer electrons. When we number these columns, we are ignoring this block in the middle. This is called the transition metals. And then there's this staircase line that goes down from boron. And on some periodic tables this might be emphasized, because on the left hand side of it we've got the metals, and on the right hand side we've got the non-metals. Group 1 is called the alkali metals, and hydrogen is technically not a metal, but it's grouped here because of the rule that elements with the same number of outer electrons are in the same group. The rest of these are metals that are very reactive and react very vigorously with water. When they do so, they turn water alkaline. These metals are also very soft and dull quickly. Group 2 is the alkaline earth metals. They are also very reactive with water and air, but not as much as Group 1. Moving past the transition metal block in groups 3, 4, 5 and 6, we get to the next important group, which is number 7. This group is called the halogens, and they are very reactive and toxic non-metals. Also, they react with alkali metals in group 1 to form salts, but we'll look at that more in a later lesson. Group 8 is also called group 0, and this is the noble gases. These are very unreactive non-metal gases. Atoms are the simplest building blocks, and each element contains only one type of atom. There are 3 different particles within atoms, called protons, neutrons, and electrons. Protons and neutrons are found in the nucleus, and electrons orbit the nucleus in electron shells. As you can see, protons have a positive charge, neutrons hold no charge, and electrons have a negative charge. Also, protons and neutrons have a mass of 1, and electrons are almost massless because their mass is so small, so it's commonly taken as 0 at this level. Because the nucleus holds protons and neutrons, it is positively charged, but because neutral atoms have the same number of protons and electrons, it is neutral overall as the charges cancel out. As mentioned before, elements with the same number of outer electrons have similar properties, and this is why they are grouped together in the periodic table. Each shell around the nucleus will hold a specific number of electrons, and these shells are filled from the center outwards. The first shell will hold 2 electrons, the second 8, third 8, and fourth 2. These shells will start holding more electrons as you progress to elements with higher atomic numbers, as you can see from electron arrangements if you have a data booklet. Here is an example of a potassium atom, and you can see that it follows the filling rules: 2 electrons, 8 electrons, 8 electrons, then 1 electron here because their electrons have run out. So potassium atoms have 1 outer electron, so we're in group 1, the alkali metals. Elements all have valency numbers. These numbers are also sometimes called combining powers because they indicate an element's ability to combine with other elements. For the main groups, an element's valency depends on the group that it's in, as you can see here. This is because elements with the same number of outer electrons have the same valency, and we know that elements with the same number of outer electrons are found in the same group. Transition metals can have more than one valency though. You might see that Roman numerals for a transition metal might be different in 2 different compounds, as you can see in these 2 examples. By the way, a compound is a substance that contains 2 or more elements bonded together. So in these 2 compounds, the transition metal, in this case copper, has 2 different valencies. In copper 2 chloride, copper has a valency of 2, and in copper 1 fluoride, copper has a valency of 1. Nuclide notation is useful for displaying information about an element because it shows the symbol, the atomic number, and the mass number for the element. The mass number is the one on top, and its value is the number of protons plus the number of neutrons in an atom. This is because protons and neutrons are the particles with the mass of 1, so these 2 make up basically the entire mass of the atom. The atomic number is the number below, and this is the number of protons in the atom. If the atom is neutral, it will also be the number of electrons because these are equal. Here's an example where you may be asked to find the number of protons, neutrons, and electrons in the atom from the notation. So the atomic number is 9, so we know that there are 9 protons. Also, because there's no charge on this, there will also be 9 electrons. The mass number is 19. So to find the number of neutrons, we do 19 minus the number of protons, which is 9, to get 10 neutrons. So there are 9 protons, 10 neutrons, and 9 electrons. Atoms are the most stable when they have a complete outer shell of electrons. So if the outermost shell has a capacity of 2 or 18, the atom would be most stable if it had 2 or 18 electrons in it. We already know that the noble gases are very stable, and this is because they all have full outer shells. Atoms may donate or accept electrons to achieve this stable electron arrangement. When they do this, they gain a positive or negative charge because they now have more or less electrons than before. This means that the electrons and protons aren't equal in number anymore, so they don't cancel each other out, and the atom gains a charge. When an atom accepts one or more electrons, it becomes a negative ion, because electrons are negatively charged and the atom is gaining more negative charge than it has positive. Conversely, when an atom donates one or more electrons, it becomes a positive ion, because the atom is losing some negative charge, so there will be more positive charge than negative in the atom. Here's what nuclide notation looks like for an ion, and remember that because it's no longer neutral, the atomic number is only equal to the number of protons. To find the number of electrons, you have to do the atomic number minus this charge here. And also, if this was a 2 negative charge, you would add 2 to 12, but it's positive, so we're going to minus it. And that gives us 10 electrons. Here is a visual for an atom donating an electron to gain a stable electron arrangement. So in this case, lithium, which has one outer electron, is going to donate this electron and become a positive ion. So now it has a full outer shell of 2 electrons here, and it is a 1 positive ion because it's donated 1 electron. Atoms of the same element can have different numbers of neutrons. This won't affect the charge on the atom, but it does mean that these atoms will have different mass numbers. Isotopes are defined as atoms with the same atomic number but different mass numbers. This is the case because atoms have the same number of protons but different numbers of neutrons. Most elements have 2 or more isotopes, and the physical properties of these isotopes will vary from the original atom, so their density or melting point might vary, but they act the same in chemical reactions. Here's an example of 2 isotopes of chlorine. You can see that their atomic numbers are the same, 17, but chlorine-37 has a larger mass than chlorine-35. This is because chlorine-37 has 2 more neutrons. RAM stands for relative atomic mass. It is an important value because different atoms of the same element can have different masses, and we know that these are called isotopes. Therefore, an average mass must be taken of isotopes, and the proportion of each isotope present is taken into account with RAM. Proportion just means how much of each isotope there is. Here's an example of the RAM of lithium, and because the atomic number is closer to 7, that means there is more of this isotope present in the sample. In this second example, the RAM of bromine is 80, and as you can see, this value is right between the atomic numbers of both of these isotopes, so the proportion of these isotopes in the sample are equal. That's all of the information that I'll cover in this lesson. On this slide, we have a number of questions related to the theory that you've learned in this lesson, and on the next slide are the answers.